Welcome to section 15.2. In this section, we're going to be looking at the concept of double integrals, but this time not over just rectangular regions with constant bounds, but rather looking at general regions where we can have other types of functions involved. So in the case where we have a function f of xy greater than or equal to 0, so we're looking at the idea of volume above the xy plane, we can still interpret the double integral over d as the volume of the solid that lies above d and under the function f of xy. But we're using the value d this time instead of r, because r represents a rectangular region. D will represent just a general region in the xy plane. These types of regions can be broken into two different forms. So we're going to look at those right here. So this is a type 1 region. In a type 1 region, we have a region where y is bounded between two functions of x, and then x is bounded between two constants on the edges. So you can see a few different examples down here of these different types of regions. So you can see that you have a function of x here, a function of x here, and y is being evaluated between the two of them. And then the edges are set, right, or cut off by the x values going from a to b. Same thing here, same thing here. The way that we write this using a double integral, we set up double integral of f of xy dy dx, where y is going from g1 of x to g2 of x, and x is going from a to b. So we evaluate this integral first with respect to y. Once we are done with the antiderivative, we're going to substitute in these values. These are not necessarily numbers anymore. These are functions of x. So you're going to be replacing all the y's in your antiderivative with functions of x. Once that process is done on the inside integral, now you will have an integral from a to b of a function with x's in it, dx. So again, just a regular single variable, single integral, like a Calc 1 integral. Now, the labels on these different types of regions, I want to make a little note here, because I don't necessarily like using the type 1 style of label, because I think it can get confusing, especially as we get a little bit later in the chapter. We're going to see other types of regions and other type 1, type 2, type 3, that kind of stuff. And I think it just can get a little confusing. So the way that I like to think about these regions, the type 1 region is a region where the integration is occurring vertically. So we have vertical integration. Okay, so we integrate between the two functions vertically, right, from bottom to top. Same thing here, same thing here. And then again, the constant bounds are setting the edge. For a type 2 region, you can see it's the same idea, except in a type 2 region, x is between two functions of y. So we're going between two functions of y horizontally. So a type 2 region, this is going to involve horizontal integration. So we integrate x between two functions of y horizontally, and then y is setting the edge from c to d. So we get our double integral of f of xy dx dy, with x going from h1 of y to h2 of y, and y going from c to d. So that, just like in the other case, once we're done with this innermost integral, all of the x's will have been replaced by these functions of y here. So we will just have a single variable integral in terms of all y's at the end to evaluate. A good rule of thumb for these types of double integrals, because obviously these are not all constants anymore. Now we have variables in the bounds on all of these. Whatever integral has the functions, has the variables in it, that should always be the inside integral. Okay, so the outermost integral, so this one down here, so this one c to d, or up here, it was this one, a to b. The outermost integral should always have only constant bounds. Okay, so again, the outermost integral should only have constant bounds. Because by the time all is said and done, we want this outer one to evaluate to a number. Because remember, we can interpret this in terms of volume. So we should be getting out a numerical answer. So the setup for the integration is a little bit different here, just because we do have to take into account the functions, what direction they're going, top and bottom, left and right, that sort of thing. So when it's vertical integration, it's a little more straightforward. We can see very quickly, bottom function and top function. When it's horizontal integration, we're always going based off of the axis, so going out from the axis. So that means we always go left to right. So h1 will be the lower function and h2 will be the upper function. Okay? Or if you want to think about it as the inner and outer functions. Let's take a look at some examples. So evaluate double integral over d of x plus 2y dA, where d is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. So as you can see, I've got the graph up here already for us to refer to, but we're going to need to set up the double integral. We already know what goes inside the integrand, so that's not a problem. We need to figure out the bounds. Okay, so we need to figure out the order of integration here. Is it dx dy or dy dx? And then figure out where the bounds are going to go. So for these two functions here, so we've got y equals 2x squared and y equals 1 plus x squared. We need to figure out which function is on top and which one's on bottom. Now, of course, when the graph is here, that's pretty easy for us to do, but imagine you didn't have this here. We would need to figure out which one is on top and which one is on bottom. To do that, you can either, if you have an understanding of these functions, you can figure out fairly quickly which one's on top, because in this case, this parabola starts at the origin down here. This one is a parabola shifted up 1 unit because of this +1 here. So this one is clearly on top, and this one would be on bottom. But if you weren't sure, so I want to make a note here. So note, if you aren't sure, fix this. If you aren't sure which function is on top, come on now. If you're not sure which function is on top, it just really doesn't want it to spread out. Sorry, I'll fix that in just a second. Plug in a value from the interval to see which has the higher output. So let me just stretch this back out. All right. So if you aren't sure which function is on top, plug in a value over this interval to see which one has the higher output. So in other words, like if you plugged in 0 here and you got its output, that one would give you a 0, but this one would give you a 1. This one's value is higher, meaning it's the function on top. Okay, so a lot of times when we're working with functions, we do understand, like with these parabolas, we understand why this one would be above the other. But if you're ever not sure, just substitute in a value on this interval, and whichever one has the higher output, that's the one on top. So we need to, first we can identify the direction of integration. This one, of course, is going vertically. So we're going to have, vertical integration, which again, if we're keeping with the labels, this would be type 1. So we have it's between two functions of x. Okay, and that's also a good technique to determine whether it should be vertical or horizontal, depending on what variable the functions are written in terms of. We can always remanipulate it, but in this case, it seems pretty clear that these are supposed to be functions of x. So we need to get the bounds. Now the y bounds will be the functions. The x bounds, however, need to set the edge. You need to set this boundary here on both sides of the region. These are not given to us. These are something that we have to find. So we need to find the points of intersection between these two curves. And again, imagine you don't have the graph here. So we would go ahead and set these equal to each other. So we get x squared equals 1. So x is plus or minus 1. So our double integral over d of x plus 2y dA, we're going to get our double integral, and we're integrating vertically, so it's going to be dy dx. Okay, y comes first, so we're going vertically from the lower function 2x squared to the upper function 1 plus x squared, and then the x values setting the edge over here are going to go from negative 1 to 1. And now when it comes to evaluating the integral, we just go one integral at a time. So we're going to set up this middle one, this inside integral. So we'll leave the outer one alone. Don't neglect it. The outer integral needs to stay there, but it can just stay there. It doesn't need to actually do anything at the moment. Let's see. So if we take the antiderivative with respect to y, we're going to get xy plus y squared from 2x squared to 1 plus x squared. Dx is still out there. So from here, we would substitute in the 1 plus x squared in for all of the y's right there. So that would give us x times 1 plus x squared plus 1 plus x squared squared. And then we would substitute in 2x squared into both of those as well. I'm just going to skip over that algebra and just cut to the chase here. We get negative 3x to the fourth minus x cubed plus 2x squared plus x plus 1 dx. So we just employ fundamental theorem of calculus, okay, just f of b minus f of a. And now we have a function all in terms of x, okay, and x only. So now we can go ahead and just do single variable calculus on this. So that's going to be negative 3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x to the 3rd plus 1/2 x to the 2nd plus x, all evaluated from -1 to 1, which again, I'll save you the hassle of us trying to plug and chug all of those numbers. We end up getting 32/15 as the value of that double integral. So we set this one up using the vertical integration, and we were able to evaluate using our standard integration techniques. For this next example, and I'm not going to scroll all the way down just yet because we're going to look at it first. Find the volume of the solid that lies under the paraboloid z equals x squared plus y squared and above the region D in the xy plane bounded by the line y equals 2x and the parabola y equals x squared. So I want to pull up this graph here. So as you can see, we've got this paraboloid, x squared plus y squared, and we've got the region in question. So you can kind of see it down there. So that region is bounded by y equals 2x and y equals x squared. We're trying to find the volume of the solid that is below the paraboloid but above that region. So if we took the region and extended it, so if I extend that up, see how that's making a cut along the paraboloid? And then I take the green one and I do the same thing. It's also making a cut, and it's filling in that region there. The piece on the paraboloid that leaves is right here. So you can see if I line this up vertically that they line up right there. So we've got the volume under this red piece of the paraboloid but above that region. So that's this section right here. So we're looking for the volume of that object. Let me get rid of the rest of the paraboloid. So this object right here. So this is what the double integral is giving us. It's giving us the volume of this solid. And we find that by integrating under the surface, so under the paraboloid, that's going to be our integrand, and then above the region in the xy plane, which again is the region with the green and purple right there. So this is the region that we're trying to find the volume of. So you can see I've got the 2D region defined right here. Now when it comes to setting this up, we can go ahead and notice that, right, this is y is a function of x, y is a function of x. We can go ahead and integrate vertically, right, from bottom function up to top function for this region. So this would also be vertical integration. So we're going to go double integral of x squared plus y squared dy dx. And then y, going vertically, is going from the parabola up to the line. So that's going to be x squared up to 2x. And then the x values are going from the left intersection point to the right intersection point. So if we look for the intersection points, again, same idea. We just set them equal to each other. Subtract, factor. We end up with x is 0 and x is 2 for those bounds. So x is going from 0 to 2. Then we can go ahead and integrate so that outside integral will stay there. The inside, with respect to y, we're going to get x squared y plus 1/3 y cubed from x squared to 2x dx. And when we evaluate this, so the 2x goes in place here and here, and then the x squared goes in place here and here. So it gives us some powers. And then if we combine any like terms, etc., we're going to end up with negative 1/3 x to the 6th, negative x to the 4th, positive 14/3 x cubed dx. And then we can take the antiderivative of all of this. That's negative 1/21 times x to the 7th minus 1/5 x to the 5th plus, that would be 7/6 x to the 4th if we simplify. All evaluated from 0 to 2, which ends up giving us 216/35. So we end up with a pretty big fraction. But this one does give us a volume. So this is the volume, again, that was under the paraboloid, just above this portion of the xy plane. That was above this little graph here. Now, the interesting thing about this example, and why this is a kind of a good one for us to try here, is because this region does not only have to be done as a type 1 or vertically. Because if you'll notice, like vertically, we go from parabola up to line. But if we go horizontally, so like from left to right, we go from one left function over to one right function. So from line to parabola. And we could evaluate this horizontally as well. So this region could also be evaluated horizontally. But if we're going to set it up this way, squared plus y squared, this would be dx dy, like that. In order to do this horizontally, we would need, instead of y going between two functions of x, we would need x to go between two functions of y. So we would have to rewrite these curves. So like for this one, instead of y equals 2x, it would become x equals 1/2 y. And for this one, instead of y equals x squared, we would get x equals the square root of y. And we would have x going from the line over to the parabola, so not the other way around. So we would go 1/2 y up to square root of y. And now y, we would need to get its intersection points. So we would take 1/2 y equals rad y. So we would get, if I multiply, if I square both sides, multiply through, we get y squared equals 4y. So we get y times y minus 4 is 0. So y is 0 and 4. So we get the dy integral going from 0 to 4 this time, because we're dealing with the y values, so from here up to here vertically. And I'll leave this one as an exercise for you guys. So we know that because it's the same region, that we will get the same answer. So we've just redefined it here. So you're more than welcome to give this one a try if you want to practice with this type of integration. But notice the important difference here between this section and the last section. In the last section, we were dealing with rectangular regions only. And with Fubini's theorem, it said you can just switch the order of the integrals anytime that you want, right? Order of integration doesn't matter. dy dx, dx dy, it's all the same. When it's not a rectangle, so it's a region like this, notice these integrals, in order to switch them, we had to make some pretty significant changes to the integrals in order to be able to do this. So if you're not working with a rectangular region, you can't just switch them. You can't just flip the order of the integrals. You can't just switch the variables around and like just flip, turn an x into a y, that sort of thing. You have to look at the region and then physically make the changes to go horizontally here. So because like on this one was going parabola to line. This one's going line to parabola. This one's 0 to 2. This one's 0 to 4. So there are changes that need to be made in order to make the switch and reverse the order of integration. And it's not as simple as it was with Fubini's theorem and the rectangular regions. So we have to be mindful of that. That generally speaking, you cannot just switch the order. You have to actually adjust it accordingly by looking at that region. Let's take a look at next example over here. Evaluate double integral over d of xy dA, where d is the region bounded by this line and this parabola. So for this one, I want us to look at how this would be set up, because normally our instinct is to usually integrate vertically, because that's kind of what we're used to just from calculus. If we were to integrate this vertically, we would have portions of the graph that were fine, right? We go from the line here to the parabola up here. However, once we get to this point right here, and we move over to the left, this is no longer between the line and the parabola. It's actually between the parabola and the parabola. So we would not be able to evaluate one double integral to do this. We would have to set up separate ones for separate pieces of the function. So I want us just to see really quickly. If we set up vertically, we get, so double integral over d of xy dA. We're going to have the double integral of xy dy dx. We're going to do it from parabola to parabola for the first part, but this is y as a function of x. This is y squared, so we would have to write this as y equals rad 2x plus 6. There's going to be a plus or minus there because the minus is the bottom half and the plus is the top half. So our bounds are going to go from negative square root of 2x plus 6 to positive square root 2x plus 6. And then the x values go from -3 to -1. But then we would have to also do the next portion, which is the double integral between the line and the parabola, so that's xy dy dx, from x minus 1 to the positive parabola, so square root of 2x plus 6. And then that one goes from -1 to 5. And then we would have to evaluate this double integral and this double integral separately, involving these ugly square roots in the bounds, and then we would have to add the results together. So this setup, so this is not impossible, but certainly not preferable. So setting this one up vertically is really not the way to go. Anytime that your setup is requiring you to do multiple double integrals to solve over one region, that's probably not the way to go. Whereas if we look at this horizontally, we're going from parabola up to line, and it's always parabola to line everywhere. There's no point where it switches or where we get overlap like these two. Horizontal really is the best way to do this one. So horizontal is the best setup here. So let's see, our double integral over d of xy dA. We're going to do dx dy. So our x is going to go from parabola to line. Now we do have to make an adjustment here because x is supposed to go between two functions of y. So for the line, instead of it being y equals x minus 1, we're going to have x equals y plus 1. So that's going to be the linear. And then for this one, instead of y squared equals 2x plus 6, solve for x, so subtract the 6, divide the 2. We end up getting x equals 1/2 y squared minus 3. So that'll be the new formula for the parabola. As we go from left to right, we go parabola up to line. So this is going to be 1/2 y squared minus 3 on the bottom and y plus 1 on the top. And then those are the x values. Then the y values are going between these two intersection points. So we're going to need to find those points of intersection. So just kind of do this off to the side over here. So we'll take 1/2 y squared minus 3 equals y plus 1. And then you can solve this algebraically. I'm going to multiply everything by 2 to get rid of that 1/2. So that's minus 6. That's going to be minus 8. So minus 2y minus 8. So we get y minus 4 and y plus 2. So y is 4 and negative 2. So y is going between negative 2 and 4. Right. And then, again, I'm going to leave this one if you guys want to get a little practice with this. I'll tell you the answer here. So if you evaluate the dx integral first, evaluate between the y's, and then evaluate the y integral, you should end up with 36. So we should get the value of this double integral is 36. If we take a look at the next one down here, find the volume of the tetrahedron bounded by these planes. So x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So I have the 3D graph of it right here just so we can visualize it, but I also have it interactive over here. So you can see the red plane on top, so the one that we're facing right now, that is the x plus 2y plus z equals 2. This blue one on this side, this is x equals 2y, which is the same thing as y equals 1/2 x. And you can see the line on the xy plane down there, right? It goes like up 1/2 over 1 with a slope there. X equals 0 is this side, so that's the vertical line. X equals 0, and then z equals 0 is just the xy plane. So you can see I have it down here in purple. Okay, so but we're finding the volume of this solid. And the way that we're going to be able to do that, we're going to be able to integrate under the red function, okay? Because you can see the red one is the one that's on top here. Because the blue one, this one is perfectly vertical, and this one's perfectly vertical. So the integrand is going to be that red function, which again is the plane x plus 2y plus z equals 2. And we're evaluating above that region, that triangular region down there in the xy plane. So we're going to have to set that one up as well. So our plane on top here, that's this plane right here. And for the sake of writing it as a function, I'll go ahead and solve for z here. So this is going to be z equals 2 minus x minus 2y. Then, if we look at the 2D region down here, this is the triangle that gets formed. So this is, I should say, put this the way that they wrote it, x equals 2y. This one was x equals 0 over here. This one is formed by this plane, but when z equals 0. So if we set this up when z equals 0, move that back over, and then divide away the 2, we get y equals negative 1/2 x plus 1. And then this one, might as well rewrite it. So we'll write this as y equals 1/2 x. Now, when it comes to setting this up, either vertically or horizontally, if we tried to do it horizontally, we would go from this line to this one, but then about halfway through, actually exactly halfway through, we would switch to a different line. And again, that's two separate regions then, so we'd have to set up two separate pairs of double integrals. So vertical is definitely going to be the way to go for this one. So when we set this up, so we're going to do, so volume, double integral over d under that plane, so 2 minus x minus 2y dA. If we're setting this up vertically, then we're going to go dy dx. Y is going to go from the bottom line to the top line. So that's 1/2 x to negative 1/2 x plus 1. And then x is getting bounded from 0, we saw that one, up to whatever this value is. And again, don't necessarily assume that we have the graph and access to that. But if we set these equal to each other, we end up getting x equals 1. So we get a 1 out of there. Right, so inner integral, and again, I'm not going to go through all the details of this, but we get 2y minus xy minus y squared, evaluated from 1/2 x to negative 1/2 x plus 1 dx. So there's a little bit of work to be done there. You can do a little factoring if you want, or just kind of brute force through all the terms individually. But we end up getting out x squared minus 2x plus 1. So it actually does work out not too bad. And then anti-differentiate this, so that's 1/3 x cubed minus x squared plus x, evaluated from 0 to 1, which gives us just 1/3. So the volume of the tetrahedron, the volume of that solid that is below the plane x plus 2y plus z equals 2, and bounded within x equals 2y, x equals 0, and z equals 0, that volume is 1/3. Take a look at this next example. Evaluate the iterated integral. So we have integral of sine of y squared dy dx, with y going from x to 1 and x going from 0 to 1. Now, this one looks nice on the surface just because they've already given us all of the bounds. So it seems like we just need to set this one up, like just start solving and go. The issue is that we have this sine of y squared in the integrand, and y is the first variable that we're integrating with, and that's a problem. So if we evaluate as is, we have to solve integral of sine of y squared dy, which we cannot do. We can't set that one up using like a u substitution. Integration by parts isn't going to help us there. This integral just won't work in this form. So what we need to do is we need to look at how we can possibly switch. So we need to reverse the order of integration. So let's take a look at the region. Okay. So we're going to have our xy plane here. So let's look at the information that they gave us here. So we know that y is going from x to 1. So we have y equals x and y equals 1 as these bounds here. So that's going to be y equals x is a line, like that. Y equals 1 is a horizontal line, like that. And then x is going from 0 to 1. So x equals 0 is right here. X equals 1 is right here. Okay, but it's not the whole thing. It's just the piece between these two that falls from 0 to 1. So that's going to be this region right here. And the way that this integral is currently set up is vertically. This is set up this way. And the region itself is perfectly set up for this. Like, there's no reason from the region standpoint that this can't be done vertically. The problem is the integrand, the function we're integrating under that is making this not work for us. If we want to switch the bounds, we need to revamp this region. So we're going to say or. We need to kind of reframe this horizontally instead. So we'll still have x equals 0. Oops. Okay, still the same region in question. But now if we're going horizontally, we're going from x equals 0 up to this line, which it was y equals x, but now we want to switch the variables, so we'll call it x equals y over here, with y going from 0 up to 1. So if we rewrite the double as dx dy, x is going from 0 to y is going from 0 to 1. And now this integral is definitely solvable because y is no longer the variable in this inner integral, it's x. So when we evaluate it, this is all just a constant. So we just get x sine of y squared evaluated from 0 to y dy, which will give us y sine of y squared dy. And that will allow us to solve. So you could set up like a u sub for this one. U is y squared, du is 2y dy. So divide the 2. So you would get sine of u times 1/2 du. So we would get negative 1/2 cosine of y squared evaluated from 0 to 1. So negative 1/2 cosine of 1 plus 1/2 cosine of 0, which is just 1. Okay, cosine of 1, I don't know what that is, but we just want to leave an exact answer anyways, so that'll be the final value of this double integral. So you can see sometimes with double integrals, reversing the order of integration is not always just a matter of convenience. It's also sometimes a matter of solvability. Like we couldn't have solved this problem without switching from dy dx into dx dy. Okay, so the region plays a role because you need to look at the region. Again, you can't just swap them or just change the variable. You have to actually look at the region and actually view the transition from vertical to horizontal, see how the functions change as the order changes, that whole thing. And then we could solve with relative ease. So we're going to look at just a couple more things here before we call it quits on this section. Just some additional properties of double integrals that we can encounter. The first few here are the same ones that we saw last time. So the property double integral of f plus g is equal to double integral of f plus double integral of g. The difference is this is over a general region. So the last section, it was just over rectangles. This applies to also rectangles, but also everything else. So this is the more all-encompassing definition. Same thing here. You can pull constants out of double integrals over a general region. And if you have one function greater than or equal to another, then its double integral value will be bigger than the other one over the general region D. So all those properties still hold true. We also have this property now. If D is the union between two regions, D1 and D2, that do not overlap, the double integral over D is equal to the double integral over D1 plus the double integral over D2. Okay. And this is actually kind of similar to a Calc 1 property. It was one where you said, like, if you're taking the integral from, like, A to C here, and then the integral from C to B, that's the same thing as adding them together and just taking the integral from A to B. Same idea. So if we had, you know, like something like this, and that's like D1 and D2. If you find the value over D1 separately from the value over D2 and then add them together, that gives you the value over D, the whole thing. So this property can be helpful when dealing with regions that look something more like this. So top of the next page. So like a region like this, we could not integrate this all vertically because at a certain point, it like doubles back on itself here. So we would have different functions over different portions of the graph. But we also can't do it horizontally because there are little portions of the graph like up here that double back on themselves and other parts don't. So we can't evaluate all vertically or all horizontally. But if we look at it like this, we could take part of it, split it into D1 and D2. D1 gets integrated vertically, and then D2 gets integrated horizontally. And now we could evaluate them separately and just add their results together, and that would avoid any overlaps or any issues with this type of region. The next thing to look at, this is a pretty helpful and interesting property that connects us back to a little bit of the work we did in Calc 1 with integration. So this says, if we integrate the constant function f of xy equals 1 over the region D, this actually gives us the area of D. So if we find, again, remember that the double integral gives us volume, but if you find the volume under the function 1, that volume will be equal to the area of D. So we know that volume is double integral over D of 1 dA in this case, right? If we're integrating under 1, then that's going in the integrand. But we know volume is also, we would take the area of D times the height of the object. So picture like, you know, like a cylinder, something like this. We take the area of the circle times the height, and that gives us the volume of the whole thing. Area times 1. Which is just the area. So the volume in this case, because the height is 1, is just the area. So the double integral of 1 dA is just the area of D. Okay, so this property allows us to use a Calc 3 technique of double integration in order to find a Calc 1 idea, that's area under a curve or area between two curves. So we'll see how this property does extend further, but this gives us kind of our first kind of connection, our tie back to finding Calc 1 values using Calc 3 techniques that are much more powerful than what you had back in Calc 1. One direct result of this property, so in kind of our last idea here, if you have a function that is bounded below and above by little m and big M, then the double integral of the function, which is again the volume under this function, is going to be bounded between little m times the area of D and big M times the area of D. Basically, we have some function f that is bounded between big M and little m. And if we take those values times that area, we end up getting volume out of here. So we're basically just saying that the area under this surface here, or excuse me, the volume under that surface is bigger than this one, but smaller than this one, which is under the whole thing. Okay, so we can use this property to also bound integrals that maybe we don't know exactly what their value is, or maybe we can't solve them directly, but we do know that they're bounded maybe between two constants. We could use this to approximate integrals that we couldn't solve otherwise. So these techniques do have some merit in fields with application and just even in the sense of approximation. So, but that is the end of section 15.2. That is our introduction to double integrals over general regions. When we come back in the next section, we're going to be looking at new types of regions for us to evaluate double integrals with respect to, and I will talk to you all in that next section.